In this video, we're going to talk about another type of stereoisomers. So we've had enantiomers so far, and we're going to talk about diastereomers, and then I also want to talk about meso compounds. Before we do that, though, there is a way to determine the number of stereoisomers for a molecule. So the number of stereoisomers possible what we're going to do is we're going to take 2 and we're going to raise it to n, where n is equal to the number of chiral centers. And this is really nice because it's not out of the realm of possibility that I give you a molecule and I say draw all possible stereoisomers. So I won't tell you how many to draw, but you can figure that out, right? Figure out how many chiral centers you have, take 2 and raise it to whatever that is. So if I only have 1 chiral center, 2 raised to the first power, I'm only going to draw 2 things total. If I have 2 chiral centers, I can draw 4 possible things. Example, so I'm going to draw a big molecule, so just kind of bear with me here. What I'm drawing is actually the structure for penicillin. As we draw, it'd be good to be thinking about functional groups too. Maybe we'll add that. What kind of functional groups do we have? Get the sulfur in the ring. It's actually a functional group that includes sulfur that we didn't learn yet. We will add it in one of our chapters coming up. My bond lengths are getting a little out of whack here. Oh, CO2H, when I write it like this, our book does this a lot just because it's easier to type that than it is to actually draw what it is. But that is a carboxylic acid group, right? If you were to go through our rules for drawing Lewis structures and get the structure out of that, right? I don't have any charges. I know carbon has to have 4 bonds. You're going to actually end up with a carboxylic acid. Let me draw it out for you. A lot of times it'll draw aldehydes. Like if you're in the book, it bonded to something, it'll do like a COH. And again, I know that it can't really be in that order, otherwise carbon wouldn't have enough bonds. If I put lone pairs on there, it's gonna have a charge. So I know it can't look that way. So it would be carbon with a double bond to oxygen and then that bond to hydrogen, and I would actually have an aldehyde functional group. Okay, so I want you guys to do this one on your own. I want you to find chiral centers. So just hit pause, go try to identify all of your chiral centers, and then when you're done with that, hit play again, and we'll go through it. Okay, so remember our chiral centers have to be sp3 hybridized. So in my ring here, all of those carbons are sp2 hybridized, so I'm just going to ignore all of those. And then also remember, if it has 2 hydrogens on it, it can't be chiral because it has to be bonded to 4 different things, so that carbon I can ignore. Also, this is sp3 hybridized or sp2 hybridized, so that can't be. Oxygen and nitrogen are not carbons, so I'm ignoring those, right? I'm looking for an sp3 hybridized carbon bonded to 4 different things. So this is going to be my first one, right? It's bonded to a hydrogen, it's bonded to all of this, and then if I go in this direction, it's different than if I go in that direction. So that is going to be a chiral center. So I'm going to put an asterisk on that carbon. And this is also a chiral center, so that carbon is bonded to 4 different things again. It's bonded to a hydrogen. If I go this direction, or this direction, it's different in all of those directions. So that's also going to be a chiral center. Oops. Sulfur isn't a carbon. Next I get to this carbon here. That carbon has 2 methyl groups on it, so not chiral. This one, however, is, right? It's bonded to a hydrogen, a carboxylic acid group, And then if I go in this direction, it's different than if I go in that direction. So that is a chiral center. Coming back around, I have a nitrogen. There's a lone pair on there, but nitrogen is not carbon. This carbon here is sp2 hybridized, so it doesn't count. And I think that's all of my atoms. So I ended up with 3 chiral centers. So 2 raised to the 3rd power is going to give me 8 stereoisomers. So if I said draw all possible stereoisomers for penicillin, I would draw 8 different versions of this. I have mentioned that our carbohydrates exist, right? Our monosaccharides exist as enantiomers, right? We can have D and L versions. So I'm going to draw glucose here, and I'm going to actually draw it in a Fischer projection. Our monosaccharides actually interconverge between a straight chain and a cyclic form. So you may have only seen the cyclic form before, but they do go back and forth. So I'm drawing the straight chain, and I'm drawing it in a Fischer projection here. So all of these are chiral centers. And then CH2OH. And this one is actually D-glucose. So what we want to know are how many possible stereoisomers for this. So again, we're just going to mark our chiral centers, and I already gave this one away when it's in a Fischer. It's easier to tell, but those are all chiral centers, right? If I look at the top one, I have a hydroxyl group, a hydrogen, this, and then this whole bottom half or bottom part of the molecule, right, which is different than my aldehyde group. I might have called that by the wrong thing, but that is an aldehyde group on the top. So anyway, the bottom is different than my aldehyde group, hydrogen, and my hydroxyl. And then if I look at the second one, again, I have this, and then this bottom half is different than this top half. And you can continue, but all of those are chiral centers. So if I was to take 2 and raise it to the 4th power, because I have 4 chiral centers, right, n is equal to 4 in this case, I'm going to end up with 16 stereoisomers. And actually, all of them are not glucose. Only 2 are glucose, the D and the L, the enantiomer of this. If I was to draw the mirror image of this, it's still glucose. If I was to draw the other stereoisomers besides the one enantiomer, it's actually not going to be glucose anymore. So like galactose and other aldohexoses are just stereoisomers of this one. If you take biochemistry, you'll learn about all of that stuff. If you don't know what an aldohexose is right now, you don't need to, you're fine. I just wanted to do another example of determining the number of possible stereoisomers. So we are going to actually do one next where we draw them all. I'm not going to make you draw 16 of them because that's just cruel. So we're going to draw an amino acid. I also said that our amino acids exist as different stereoisomers. So we're going to draw a threonine. And I'm just going to draw a straight chain form to begin with. So I have an amino group on one end, and then carbon, and then this is a carboxylic acid. So they're actually called amino acids because I have an amino group, right? Here I have a nitrogen, I have a nitrogen bonded to a carbon, so that's an amine functional group. And then I have a carboxylic acid functional group, so amino acids. So what we're going to do is we're going to draw all possible stereoisomers for this in a Fischer projection. So we're actually going to do lots of things. So first one, how many stereoisomers are possible? We want to know that first. We're going to draw all possible stereoisomers in Fischer projections, we are going to assign configuration, so that's the R and S, to all chiral centers. And then we're going to label enantiomers and diastereomers, which I have not defined yet, but we will do it as we go. So enantiomers, remember we said, were our stereoisomers that are non-superimposable mirror images, right? We said they have opposite configuration at all chiral centers. Diastereomers are going to be are going to be stereoisomers of each other, but they're not going to be mirror images. So these are, remember, mirror images that are non-superimposable. They were superimposable, they're the same thing. So non-superimposable mirror images. They have opposite configuration at all chiral centers. Diastereomers are not mirror images. They're still stereoisomers, however. And they're actually going to have opposite configuration at least one, but not all chiral centers. If they had the same configuration at all of the chiral centers, then they're actually the same molecule. They're not stereoisomers at all. So these are going to have the same configuration. Let's actually say the opposite. Let's say it backwards. They're going to have the opposite configuration at least one, but not all, because if they were opposite at all of them, then they would be enantiomers, right? But it has to be opposite at least one, because if they were all the same, right, then it would be identical. So opposite configuration at least one, but not all chiral centers. And then we might as well add it here. We can add it later too. But remember how enantiomers had the same physical properties, except they rotate light in opposite directions, right? One would rotate it to the left, the other enantiomer would rotate it to the left, or to the right, opposite. Diastereomers, these guys are actually going to have different physical properties. So the boiling points, melting points, they're going to be different. So different physical properties. So you could actually go into lab and like separate them based on melting point, boiling point, etc. Remember, with our enantiomers, they have the same physical properties with the exception of their light rotation. So different physical properties for diastereomers, same with that one exception for enantiomers. The boiling point of the pair of enantiomers is going to be the same. It's going to be different for my diastereomers. Okay. So we have a lot to do. How many stereoisomers do we have? So we're going to figure out how many chiral centers we have, and then raise 2 to that number, and then we're going to draw all of them in a Fischer projection, which isn't as bad as it sounds. I'll walk you through it. We're going to assign configuration, and then we're going to label our pairs. So chiral centers first. Again, every time we do this, I really want you to try it on your own. So if you're not seeing them right away, just hit pause and then try it. So I have this one. There is a hydrogen on that carbon. So I have that amino group. I have a hydrogen. I have that carboxylic acid group. And then if I go up, that group is different. And then there's a hydrogen here also. So that carbon is also chiral. It's kind of messy. But I have a methyl group, a hydrogen, a hydroxyl group, and then that whole bottom part, right, of the molecule. So when I draw my Fischer projection for this, I'm going to draw it like that. I'm going to have 2 of them. So I'm actually going to get those asterisks out of the way so we can look. And let's actually just do one of them here. I'm not showing perspective on this. because I'm going to draw all of them, right? So what I would do, and this is just me, remember that if your hydrogen groups are coming out at you, right? They're in the horizontal position, then we have to reverse our answer. If the hydrogens are going back, if they're in the vertical position, then I don't have to reverse my answer when I do my configuration. So what I'm going to do is I'm going to choose to put the hydrogens on the top and the bottom, since I can draw it however I want. So what I'm going to do is I'm going to take, and I'm doing this chiral center first. You can make either one, the top or the bottom, but I'm going to make that this one. And then I'm going to put my hydrogen, right, the groups that I have on here. So I have to draw a hydrogen, I have to draw an OH, and then I have to draw a methyl group. And then this part is actually going to be that part. And again, because I'm going to draw all possibilities, it doesn't matter where I start. I'm choosing to put the hydrogen on top because then when I figure out my configuration, I don't have to do any reversible stuff. So I'm just going to choose there. And I'm going to redraw these down below so we can draw all possibilities. I just want to do the first one where it's sitting next to this so we can see what's going on. So now I'm going to do that bottom chiral center. Right? It has this group, and then a carboxylic acid group attached to it. And again, I have those 3 spots because I'm not given any perspective on this, and we're going to draw possibilities. It doesn't matter where I start. I'm going to choose to put the hydrogen here because then when I figure out my configuration, it's going back and I don't have to reverse my answer. I then have an NH2 group, and I'm seriously just randomly sticking it there. You could put it on the other side if you want. We're going to draw possibilities, and then I'm going to draw my carboxylic acid like this. You could draw it out, but we just went through that. So, okay. So I'm going to recopy this down below, and then we're going to draw all possibilities. So let's scroll down. I'm going to probably have to scroll up a couple times so I remember what I did. I know I put the hydrogen on the top and the bottom. And then what did I do? I have OH, NH2, my methyl group, and then my carboxylic acid group. Make sure you're bonding those to the carbons. Okay, so this is 1. Oh, we never said how many. We have, sorry guys, 2 chiral centers, right? So how many possible stereoisomers am I going to have? 2 raised to the 2nd power, good, 4. So I'm going to draw 4 things. We've already drawn 1 of them, so we need to draw 3 more. So the easiest way for me to do this, I drew 1. I'm going to now draw its mirror image. So I'm going to draw the mirror image of this first one. And I want to fit them all side by side, so I might have to squish this in a little bit. I'm just going to see if I can move this over just a tad. Okay. So I'm taking the first one that I did, and I'm just going to draw its mirror image. So the top and the bottom are still the same. I now have my hydroxyl group and my amine group on this side, and then my methyl group and my carboxylic acid group are on the other side. So those are mirror images. Even without assigning configuration, I know that those guys are going to be a set of enantiomers because by definition, that's what it is. And then they're not superimposable. Remember that these are not planar, right? When folks are learning this, usually if we're in class, someone will say, well, aren't they the same thing? Because you can just flip it over. No, because remember, these are coming forward. So if I was to take one of them, say this one, and flip it so the front is the back, so then the OH and the amino group are back on the right-hand side, instead of those horizontal positions coming out at us, they're going to be going behind, right? My hydrogens would be superimposed, but my vertical or my horizontal positions would not be. Actually, my hydrogens wouldn't be neither because instead of going back, they'd be coming out, right? Remember, these do have perspective even though we're drawing them planar. So I want to try to get rid of those wedges because you're not going to generally see it that way. So if we were to flip it over, what's coming out would be going back. So we actually can't superimpose those. Ooh, lost a carbon. So those would be a pair of enantiomers. I'm not going to write it yet because we are going to assign configuration and do that also. So for the next two, what I'm going to do is I'm going to keep one of the chiral centers the same, and then I'm going to switch the other chiral center, and it doesn't matter which one you do. So I'm going to draw another one. I'm going to keep the top and the bottom the same. Let's keep the top chiral center the same. Oops, that's a 3. And then I'm going to switch the orientation on my bottom chiral center. So I'm going to actually have the NH2 group on this side, and then my carboxylic acid group on this side. Didn't have to make those. I'm just trying to get it to fit nicely. Okay. And then I'm going to draw the mirror image of the one that I just did. And this sort of method is always going to work. If you have 3 chiral centers, draw one, draw its mirror image, flip one of the 3 chiral centers, leave the others the same, draw its mirror image, then flip the other chiral center and draw its mirror image, and you're going to end up with all of them eventually. And this is what I mean. It's not as when I say draw all of them. If you're systematic about it, it's really not that bad. So we just picked one to start, right? When we drew this one up top, as long as I had the right groups on the right carbon, it didn't matter where I put them because we're going to draw all of them. So I drew this one, and then I drew its mirror image. And then I kept the top chiral center the same, and I flipped this bottom chiral center. And then I drew this one's mirror image. And if you're systematic like that, instead of just trying to come up with all of them kind of willy-nilly, you will get the right answer. Okay. They kind of got bigger as I went across. We're going to assign configuration next, which means I need to assign priority to my groups. So looking at this chiral center right here, this is bonded directly to an oxygen, right? Here it's bonded to a hydrogen, here it's bonded to a carbon, and then this is bonded to a carbon. So oxygen has the higher atomic number. So that's going to be 1. This down here is going to be 2, right? Because this carbon is bonded to a nitrogen, a carbon, and a hydrogen. This carbon is bonded to 3 hydrogen. And then my priority, my order, hydrogen's going back, so I'm just going to keep it exactly how it is. So as I go from 1 to 2 to 3, I'm going clockwise, so that is R. And then I'm going to get these out of the way. We're going to do the same thing with the bottom chiral center. So my options, I have nitrogen, I have a bond to a carbon, a bond to another carbon, and a bond to hydrogen. So that nitrogen is going to be first. And then I need to look at the 2 carbons. So this carbon is actually bonded to 3 oxygen. Remember, if you have a double bond, you think of it as being bonded, right? You think of it as being bonded to 2 of those things. So I'm going to think of this this carbon as being bonded to 2 oxygen here, and then a 3rd oxygen here. So I have carbon bonded to 3 oxygen is how I would think of that. If I look at my top carbon, right, this carbon right here that I'm putting the big orange dot on, that carbon is bonded to a carbon, an oxygen, and a hydrogen. So carbon bonded to 3 oxygen is going to be higher in priority than a carbon bonded to 1 oxygen, a carbon, and a hydrogen. Remember, we're using atomic number for those. So let me try to get some of this off of here. So number 2 is going to be my carboxylic acid group, and then number 3 is going up. So as I go from 1 to 2 to 3, I'm going in this direction. That also is clockwise. Hydrogen is going back, so I'm just going to keep it as R. So if you're feeling confident about your ability to do that, you don't have to do the others, you just have to kind of translate it over. So if I look at this chiral center right here, it's the opposite to the one I just did. So this is actually going to be S. Now, if you got that first one wrong, you're going to get everything else wrong. So as you're learning, it probably wouldn't hurt to spot check that. And we'll do a couple checks here. Because this chiral center is the opposite to this one that we just did, right? It's its mirror image. It's also going to be S. Now, again, if you goof the first one up, then everything else is going to be goofed up too, because I'm going to base all of these on the first one. If I look at this chiral center, it's the same as the first chiral center on the first molecule. On my second molecule. So it's going to be S, right? If this one is S and this is the same, that's also S. This one is the same as this one. So that's going to be R. And then this top chiral center on my last molecule is the same as the first one. So R. This is the same as this. So S. Again, if you're not confident that you did the first one correctly, I would definitely check a couple of them, because if that first one is wrong, they're all wrong now. So let's just check. Let's check this one here. So this is my highest priority group. Priority isn't going to change. Number 2 and number 3. So when I go in that direction, that's counterclockwise. Hydrogen's still going back, so great, S. Let's check this bottom one on the last one. Highest priority group, number 2, number 3. If I go in that direction, that's counterclockwise. Hydrogen's going back, so S. So I'm feeling okay about it. Okay, so let's call this molecule A, B, C, and D. So our next task, we're on D. It says to assign or label enantiomers and diastereomers. So remember my enantiomers, these guys are going to have opposite configuration at all chiral centers. So if I go and look, A and B are going to be a pair of enantiomers. We already said they were mirror images of each other and they're non-superimposable, so we knew that already. But if we look, the first one is RR, this one is SS. So opposite configuration at both of the chiral centers. And then we drew C, and then we drew its mirror image. So we know that C and D are enantiomers. And then double checking the configuration. This is SR, this one's RS. So opposite at both chiral centers, right? This chiral center and this chiral center are opposite. This one and this one is opposite. So those are going to be enantiomers. Diastereomers. If we go back up, it tells us that we have opposite configuration at least one, but not all chiral centers. So that's what we're looking for. So if I compare, get some of these checks out of the way, if I compare A to C, if I look at those two, in A I have RR, in C I have SR. So the top chiral center is different, but the bottom chiral center is the same. So A and C are going to be diastereomers. If I compare A to D, I have RR and RS, so the top one's the same, the bottom one's different. It's actually all my other combinations, right? If I compare B to C, so B is SS, C is SR, so the top is the same, but the bottom is different. And then if I was to compare B to D, B is SS, D is RS, so the top is different, but the bottom is the same, right? Opposite configuration at least one, but not all chiral centers. If it was the same at all, they would be the same, right? They wouldn't be stereoisomers. And if it was the opposite at all, they would be enantiomers. So our other options are our diastereomers. The last one I want to talk about are meso compounds. And meso compounds are compounds that are achiral, but they have chiral centers. So remember kind of towards the beginning of this chapter, we said that if you had no chiral centers, it was going to be achiral. If you had one chiral center, it's going to be chiral. If you have two chiral centers, it could be chiral or achiral. And we said that achiral molecules will have that plane of symmetry. So this is something that has chiral centers. It needs to have at least two of them, and it has a plane of symmetry. So compounds that are achiral, they actually would be superimposable. They're actually the same thing. So molecules that are achiral but contain chiral centers. And again, they have to have at least two chiral centers. Diastereomers do also, right? There's no way to have a set of diastereomers and only have one chiral center, because they have to be the same, right, at like one of them, but different at least one of them, right? There's no way you can be different at one but not all if you don't have more than one. So both diastereomers and meso compounds are going to have more than one chiral center. So meso compounds that are achiral, right? They're not optically active. They're not going to rotate light, but contain chiral centers, right? They do contain a plane of symmetry. So kind of an example for us. Let's stick a chlorine in the middle for fun. If I was to look at this one, I do have two chiral centers, right? That carbon is bonded to hydrogen, a bromine, this methyl group, and then this whole part of the molecule. So it gets an asterisk. And then the other carbon that has the bromine on it, right? It's bonded to a hydrogen, a bromine, a methyl group, and then the left part of the molecule. So it has a chiral center. This is not a chiral center, right? It has a chlorine, a hydrogen, but if I go this way, it's actually the same as I go that way. So that's not a chiral center. Be careful for something like that. If I asked you how many stereoisomers are possible for this, you're going to say 4, right? 2 raised to the second power, not 8. Right? There isn't 3 chiral centers. And this one does have a plane of symmetry. This would be a meso compound. We could actually cut it right through that chlorine. There's a hydrogen there too. One coming out, one going back, and we would slice right through those. Right? This half is the same as this half, which is why that carbon that the chlorine is bonded to is not chiral. So I have 2 chiral centers, but I have a plane of symmetry, so this would be a meso compound. Right? It's not chiral. And we can let's actually draw all of our possible stereoisomers for this, like we did in our last problem. Put that chlorine back on there because we're going to need it. Okay. So I have 2 chiral centers. I'm going to draw 4 things again. So I do have to do 3 of these this time, because even though this is not a chiral center, that carbon with the chlorine on still exists, right? So I do have to put that in there. And then I'm going to put my hydrogen on the top and the bottom again, because then when I assign configuration, my lowest priority group is going back. Again, you don't have to, but I just think it's easier. And then I have a bromine and a methyl group. It doesn't matter what sides you start with, because we're going to draw all possibilities. So I drew my one. I'm going to now draw its mirror image. So we're doing just like we did in the last problem. So bromine, hydrogen, bromine. For the carbon with the chlorine on, it doesn't really matter what side you put the chlorine or the hydrogen again, because it's not chiral. So if you want to draw them, the same every time, like I drew the mirror image because I was just doing the complete mirror image. I like my mirror images to actually be mirror images, but it doesn't really matter with that one. I'm going to switch now the configuration on one of my 2 chiral centers. Again, it doesn't matter which one, because I'm just going to do the other one also. So I'm going to keep the top one the same. And then I'm going to switch this bottom one. And then I'm going to draw its mirror image. That looks like an A. It's a C and an L. All right, and then that should be all of them. So it's kind of the same method, right? We drew its mirror image, we switched the configuration on one of the two chiral centers, and then we drew its mirror image. I'm gonna do the configuration pretty quickly, but again, I want you to do it yourself, so please just kind of hit pause if you want, and then do it on your own. So 1, 2, 3. If you have questions, you can always ask me. So that's clockwise, so this is R. And then 1, same 2, 3. And that is counterclockwise, so that's going to be S. And then I'm going to trust that I did it okay. Maybe we'll check 1 just to be sure. I'm just looking at the ones that are the same. It's a matching game at this point. And then R. So let's just double check. This one, 1, 2, 3. Sometimes I get my clockwise and counterclockwise goofed up. I actually have to think of a clock. Am I going like time? Am I going the wrong way or not? And then we'll check this one also. 1, 2, 3. And that's clockwise, so R. So I'm feeling okay about it. Hopefully you guys are too. And then enantiomers, we actually have meso this time, so we have to be careful. Meso, and then diastereomers. So when you're looking at the enantiomers and the meso, you have to be careful for this one, because meso ones are going to have opposite configuration at both chiral centers also, but they're going to have a plane of symmetry. So let's give these numbers, I forgot that, or letters, A, B, C, and D. So enantiomers, C and D are going to be enantiomers, right? C is SS, D is RR, so opposite configuration. And they are mirror images of each other, and they're not superimposable. Right? The only way to try to line them up, try to get groups on the same side, was to take one of them, so I'm going to take D, and then flip it front to back. But if I do that, the groups that are coming out, my horizontal positions are now going back, my vertical positions that were going back are now coming out. So I can't superimpose them because it's the opposite on the one I'm trying to superimpose it on. If I look at B, A, and B though, I do have opposite configuration, R, S, and SR. So they look like they're enantiomers, they're mirror images. It's really tempting to write down enantiomers on this one, but these ones are actually meso. I can superimpose them. And how I can superimpose them, we can't go front to back, because again, then the groups that are coming out are going back, and the groups that were going back are coming out. But I can do it like head over heels. I can flip this up, and I can flip this down. So everything that's coming out at you is still coming out at you. Everything that's going back is still going back. But if I flip it head over heels, I can line that up. I can't do that with these two, because when I do that, if I flip this one down, now bromine is going to be over on this side, right? It's going to be the bottom carbon, but it's going to be on the wrong side. But I can superimpose A and B. They are superimposable. And then they have that mirror image, right? They have that plane of symmetry, I should say, right? And it cuts right through these atoms, right? That top half is reflecting to the bottom half. So A and B are not enantiomers, they're meso. If they're meso, they're actually the same thing. So when I do diastereomers, I'm actually going to think of A, B, and right, they're superimposable. They're essentially the same. So I'm going to think of them as the same. So A, B, and C, right, are going to be diastereomers. And then A, B again, I'm lumping together, and they're diastereomers of D. So those would be my combinations for this one.